Angela Rasmussen from the University of Utah Department of Electrical and Computer Engineering. And this is an example with a series connection for RLC when it's moving and it's an overdamped transition. So this is the circuit that we have. The steps that we want to go through is to determine is it series or parallel, and then determine alpha and omega naught, compare the two, determine critically damped, overdamped, or underdamped, and then find all of the unknown variables for that general equation. And then that will give us VC or IL, and then we're going to plug in all those unknowns to get the equation. And then from there, if we want to still determine another voltage or current in the circuit, we're going to use that solution to determine the others. So first step is to look at, is it series or parallel? And that is going to be in the final position of the circuit. So look at the final position. In this case, the circuit or the switch is open. And so here you can see that the L and the C are in the same branch, and so they are in series. So we have a series configuration. The next step is to find alpha, which is going to be RTH over 2L. And in this case, it's going to be, again, the final circuit. You're going to find the equivalent resistance that the capacitor sees. And so finding it at the capacitor location, it's the final circuit, so we keep that switch open. Inductor becomes a wire. The current source becomes an open, and then A to B is going to be for the capacitor, and you can see it's 0.52 plus the 0.1 to give 0.62 over 2, and L was given as 0.5. And so this gives a value for alpha of 6.2 nepers per second. And then omega naught is 1 over the square root of L, which was 0.05, times C, which is 1.8. And so that gives a value of 6 nepers per second. And then from here we need to compare, and hopefully you can see that it is that alpha is greater than omega naught. And so we move to the table, which shows that it's in an overdamped situation. And so for overdamped, we need to find the final value for the capacitance, the initial value, the roots S1 and S2, and then IC initial value. So with this, I usually start at the initial value, so that's going to be right before the switch happens. It's going to be sitting for a long time, so that becomes a wire. The capacitor becomes an open, and let's see, the switch is right before it opens, so it's going to be closed. And with that, you can see that there's no current here, which means there's no voltage there. And so I like to do node voltage, and so this is going to be the same voltage up here as across the capacitor, so VC. So this branch current minus 4 milli, this branch is VC over 0.1, and this branch is VC over 0.1, and solving that gives me a VC value of 0.2 millivolts. And then IL is going to be also needed to be determined to find the initial values. So IL, you can either see that 4 milli is coming in and splits evenly, so 2 milliamps for IL, or you can use that VC over 0.1, which gives me 2 milliamps. So IL will be 2 milliamps, and then I do the initial value is going to be right after the switch. And so I replace the current source with this 2 milliamps, and I replace the voltage or the capacitor with the voltage source of 0.2 millivolts, and then the switch is actually open. So this will be my initial circuit, and I need to find this IC of 0 here. And so in that case, this is going to just be given by the 2 milliamps, which is what was flowing through it. And then VC of 0 will be this 0.2 millivolts. So I am going to just take note, my VC of 0 is 0.2 millivolts. My IC of 0 was 2 milliamps. So now I need the final value. And so the final value for the capacitor is going to be, it's going to be open here. It's going to have sat for a long time, so capacitor is open and inductor becomes a wire. And so VC of infinity is going to just be the voltage across the resistor, and so 0.4 millivolts. So that will be my value at infinity of 0.4 millivolts. And so the other unknowns that we need is S1 and S2. So I plug in the values for alpha and omega naught. And that gives me an S1 of minus 4.64 neighbors per second. And a value of minus 7.76 neighbors per second for S2. And so I can now write my VC equation. So VC of t is going to equal A1. So actually I'm going to back up. I still need A1 and A2. And so A1 is 1 over C, and C was 1 over 1.8 for the C values. So A1 is going to be 1.8. And IC of 0 was 2 milli. And S2 is a minus 7.76. And VC of 0 is 0.2 milli. And VC at infinity was 0.4 milli. All over S1 minus S2. And so this gives me a value for A1 of 0.66 millivolts. And A2 is similar, 1.8 times 2 milli. And then minus S1, which is minus 4.64. 0.2 minus 0.4. And all over S1 minus S2. Or S2 minus S1. So S2 is a minus 7.76. And so this gives a value for A2 of minus 0.86 millivolts. So now I can plug it into the equation for VC of t. So VC of t is going to be, let's see, the A1, 0.66 milli, E to the minus 4.64 t, which is S1, minus 0.86 milli, E to the minus 7.76 t. And then VC at infinity, which was 0.4 milli. So 0.4 milli. And so that will be in volts. And this is all for t greater than 0. And so this is my answer for VC of t. And so if we wanted to know another variable in the circuit, say for example we wanted to know IC of t for this circuit, we can see that IC and VC we already know is related. So we could say that IC of t is related to VC of t by C dVC dt. So we just would need to take the derivative of this, multiply it by the capacitance, and that will give us IC of t. And so in this case, that ends up being a minus 1.7 e to the minus 4.64 t plus 3.7 e to the minus 7.76 t. And that's in milliamps for t greater than 0. So this would be a way we could get IC of t from that circuit. Thanks for watching.